by an ST researcher, physician, Professor Isma. Professor Deepa Venkata obtained her bachelor's and master's degree in physics from the University of Kerala and PhD from the IIT Bombay. She has worked in Samir, Mumbai, Vivekananda Education Society, Mumbai before joining the IIT Madras. She is currently a professor in the Department of Electrical Engineering in IIT Madras. She was endowed with the Young Faculty Recognition Award of the IIT Madras in 2012 and the Fellowship of INAE in 2021. She is senior member of Editorial Board Journal of JLP. She was the Associate Vice President of Women in Photonics of the IEEE Photonics Society from 2020 to 2023. She has also served as the National Coordinating Faculty for the PMRF program of the Government of India from 2022 to 2024. She is the project lead for the Advanced Optical Communication Testbed project, which is a consortium project funded by the Department of Telecommunication, Government of India. Her area of interest are in optical communication, including capacity scaling, optical signal processing, continuous variable quantum key distribution, and microwave photonics. Today, Professor Deepa Venkatesh will enlighten us on the topic parallelism for scaling capacity of optical fiber links. Ma'am, we are honored to have you with us today. I warmly invite Professor Deepa Venkatesh to take over the session. Ma'am, the virtual stage is yours.
Thank you. Are you able to hear me?
Yes, ma'am.
Thank Professor Tangraj and all the organizers of this ATAL FDP for inviting me. It is a real honor to present the talk here. And I'm not able to see all the participants, but I'm assuming that because your videos are off, it doesn't mean that you're not listening. You are paying attention, is the assumption. So I will just assume. Yeah.
More than 180 participants.
Yes, more than I can see 166 people here. So I'm assuming that I have the attention of all of you. So the work that I'm going to present is a work, kind of combined work for the last 6 or 7 years actually. And I will summarize and present our experiments on parallelism. And a lot of this work has come because of the collaboration between other faculty in the electrical engineering department. One is Professor David Koil Pillai, senior faculty working in the area of signal processing. And the second one is Professor Lakshmi Narasimhan, who is a junior faculty. I wouldn't say senior, junior. In terms of age is what I'm saying, not in terms of their expertise. They are way better experts than I am. So he works in the domain of signal processing and machine learning. And this work has also contributions, or rather it is the PhD work of Dr. Samir, Dr. Smaranika, and Jonak, who is a current PhD student. Both Samir and Smaranika have graduated and moved on from IIT Madras. Please stop me in between, otherwise it becomes very boring and monotonous. So just maybe you can use ChatGPT to ask questions to me so that you don't have to do the thinking. I can do the thinking based on what the questions that are posed, right? So let us try to innovate on how to use ChatGPT. So the background is, of course, how critical optical communication is in our in the perspective of in general communication, all the communication that we think of wireless communication happens only in the small corner where the entire domain of wireless communication is working on how from the hand unit, user equipment, you're able to communicate, you're able to transport information to the nearest antenna, and then how these antennas are relaying the information to the antennas which are closer to the receiver, right? But what we do not physically see is the network of optical fiber that connects the transmit to the receive end, right? So from the antennas, the information goes through what are called as metro networks to what are called as core networks. It may go to satellite links. The same optical fiber link uh, connects, brings internet connectivity to the home. So, yeah. So, all this connectivity is, for example, how internet comes to your home is through an optical fiber. How data centers are connected with each other is through an optical fiber. How data centers are connected within the racks is through optical fiber, and so on, right? Just to give you an idea of what are the data rates that are typically used, in your GPON, what are called as NGPON, you have data rates from 10 to 100 gigabits per second. In your data center interconnects, you talk about greater than 100. Today, we talk about 400 gigabits per second. In mobile front haul, now front haul is a connection between the antennas to the base station, right? From the tower to the base station. And that also is through optical fibers. It is no more cables. It is no more copper cables. That goes from 25 to 100 gigabits per second. And why do you need 2500 gigabits per second there? That's because you have analog data, and the analog data gets digitized. And it is this digitized information that goes from antennas to the base stations. So especially if you have multiple, you have phased array kind of antennas and structures, you will end up having very high data rates even in short distances. And of course, core would mean that it is connecting long distances. And so that becomes what are called as backhauls or the backbone networks. And so it has to connect, it has to take information from a large number of sources and multiplex it in the time domain and transport. So that will be 1 terabits to petabits per second. Of course, now these days, I think this course will also cover about non-terrestrial networks, which are satellite networks, which are going to be very, very prevalent. And the backhaul for all the satellite networks is also through optical fiber. Now, there is a very large network which is provided in the radar domain, which is in connecting, interconnecting radars in what are called as coherent MIMO radars and so on. So what is also available is a separate optical link, and mostly that optical link is analog link and not digitized link, which is why I've kept it disconnected from all this. And optical fiber is not the only way for communication. You do have optical communication happening through free space links. You also have communication happening through what are called as Li-Fi links, right? So these are also considered as optical communication, right? And where, if you ask yourself the question, where is the largest growth of optical fiber, it turns out that this largest growth happens in the cloud-based services, and because you need very fast broadband speeds in those systems, right? And probably the largest deployment of optical fibers happen in the front haul links again, because that's where the fastest deployment of optical fibers or fastest deployment of antennas and base stations are happening, right? So now turns out that the capacity that we have is not sufficient sufficient enough if we keep scaling like this, if we keep having more and more data centers, more AIs, because I think this is a very famous statement that AI needs data. Everyone needs AI today. AI needs data. Data needs connectivity, and connectivity needs fiber, right? So finally, we are going back to a scenario where the existing fiber, deployed fiber links are not sufficient for increasing the transport capacity. So what do we do now? So what are we doing already? We are doing this already, right? So this is the electromagnetic wave, the electric field that represents the electromagnetic wave. And you know that any electric field can be uniquely represented as two orthogonal polarization. For convenience, I've taken X and Y. It could be right circular, right elliptical, left elliptical. It could be any basis. So you have X and Y polarizations. And the electric field in the X and Y polarizations can get represented as its amplitude, exponential e power. This is representing the that it is it's of course what I've not okay, what I will write here. This is the carrier e power I omega t. This is the propagation, and this is the amplitude, and this is the phase. Okay, so ax e power I phi x, ay e power I phi y. This represents the two handles that I have for modulation. So if I change my amplitude according to the bits, then it becomes amplitude modulation. If I change my phase according to my bits, it becomes the phase modulation. Typically, you do not modulate the frequency. You keep the frequency fixed. And of course, this is propagation. So this is something you cannot control, because propagation is what happens through the fiber, right? So what is shown here is, for example, what is called a 16 QAM modulation, 16 quadrature amplitude modulation. So there are 16 possible values of amplitudes and phase that you can encode the signal with. For example, this blue point is uniquely defined by its amplitude and its phase. And you could assign this as a bit sequence, let's say 0000, or maybe if we start from this corner, you can assign this bit as this point in the constellation space as 0000, because there are 16 points, so which means you can represent 4 bits uniquely. So this point is represented by its unique amplitude and its phase, which can get represented in AX and phi x. Similarly, you could have another 16 points or another 4 bits modulated on the Y polarization. So what it means is that you could have a 25 gigabaud signaling rate, but you can transmit 100 gigabits per second, because you are modulating, you are sending information corresponding to 4 bits in one symbol, right? Now you could use 6 bits, so you could have 64 QAM modulation. So 64 means 64 unique amplitudes and phases, which means that you could represent 6 bits. 2 power 6 is 64. So this is 6 bits per symbol. So you can keep increasing what is called as the orders of modulation. That is how you can increase the capacity. That is just through modulation. But you cannot keep increasing this capacity by increasing the number of bits infinitely large, because you get caught by this SNR condition, right? So you are familiar with what is called as the Shannon capacity, which is the capacity limit, the ultimate capacity. Assuming that the channel is linear, so this equation gets derived by assuming that the channel is linear, number one, and number two, the transmission is digital, right? It is in bits, ones and zeros is what you're transmitting. For that, the spectral efficiency comes out to be, which is capacity, this is available bandwidth. Capacity by available divided by available bandwidth is called a spectral efficiency, is logarithm to the base 2 1 plus SNR. So what really would happen is, if you are packing more bits in the same bandwidth, for example, you're doing 4 bits or 6 bits, between 4 bits and 6 bits, the difference is that in the same bandwidth, you had a larger data rate for the 6 bits and smaller data rates for the 4 bits. So for increased spectral efficiency, you have to pay a price on SNR. You have to work with larger SNR, which is very intuitive even from this plot, because if you SNR just, if you have more noise, it just smears around each of these constellations, which means that if you have more such points, the noise you can tolerate becomes smaller and smaller. So essentially saying that if you encode more bits per symbol, you better have a larger SNR. Okay, so that is one challenge. So unless you have very good SNR, you can't increase this capacity by making moving from QPSK to 16 QAM to 64 QAM and so on, right? So that is one challenge. Your SNR is limits the capacity scaling. Now we do have another challenge, which is, so here is the Shannon capacity, right? So you may argue that I can increase the SNR by increasing the signal power, because SNR is after all signal power divided by noise power, right? So for a given noise value, I can increase the signal power and thereby increasing the SNR. So instead of transmitting, let's say 0 dBm power, if I transmit, let's say 10 dBm power or 30 dBm power, I can increase the SNR, right? So I can beat this SNR limitation just by increasing the signal power. But the problem is that the fiber, optical fiber, is a very nonlinear medium. So as you increase the power, so here is when the SNR is increasing, and what you're trying to do here is increasing the SNR by increasing the signal power. As you increase the signal power, what happens is the capacity, which was following the Shannon theorem, which is here, starts dropping. So why is the capacity dropping? Because Shannon theorem predicts that the capacity starts increasing, it continues to increase. So why should the capacity drop as you increase SNR? And that's because your channel becomes non-linear, in the sense that it's no longer follows the condition that was imposed while deriving Shannon's theorem. I told you already that when we derive Shannon's theorem, we assume that the channel is linear. Now you're breaking that when your channel becomes nonlinear. So because of the nonlinear phase distortions, your SNR will start, your capacity will, the spectral efficiency will start dropping, which means that you are really limited by SNR, and the essentially SNR would mean signal. There is a limit to which you can increase the signal power, and as you know, when you're putting in amplifiers, you will have more and more noise added into the system, right? So I will talk a little bit more about that. But the point I'm trying to say is that you cannot imagine to just increase the capacity by increasing the modulation format, right? There is a limit, there is a fundamental limit to this. Now, these different lines are corresponding to different lengths of the fiber. You will see that for 500 kilometer fiber versus this is 8,000 kilometer fiber. 8,000 kilometer fiber, the nonlinearity kicks in much earlier because the length is large. So you will start seeing this drop. This is called as a nonlinear Shannon limit here. These lines are the nonlinear Shannon limit, and that will start dropping at much lower SNRs. Let me ask you a question. Is that the participants, how many of you have done anything to do with optical communication? Have you done any course, or are you teaching, or have you any association with optical communication? If yes, raise your hands. How many of the participants have done any course or teaching any course or read anything on optical communication? So the online participants can just raise your hands. Yeah, I can see on-site participants raising hands, but none of the online participants are participating, or none of them have done optical communication. Can any of the online participant confirm that they are actually here and listening? Oh, there are raised hands. So the raised hands mean that I think 9 of them have said that they have done optical communication. Okay.
Maybe around 30 participants.
There are 7 of them who have raised hands who have said that they are done anything to do with optical communication. Is there a way to, because I'm talking about different things in optical communication. How many of you are familiar with, next question, you can lower the hands. Next question, how many of you are familiar with signal processing? Please raise your hands if you're familiar with signal processing. Use the hand raise option, Control K or something. Signal processing. Probably 14. Okay, 20 of them. Okay. Anyone familiar with, you can lower the hands now. How many of you are familiar with electromagnetics? How many are familiar with electromagnetics? Okay, it's about 16 people. You can lower your hands. And the last question is, how many of you are aware that sine square theta plus cos square theta is 1? Please raise your hands if you're aware that sine square theta plus cos square theta equal to 1. Okay, so this is some confirmation that there are only 20 people participating, and there are different fractions of them who have confirmed. So this people who are listening are familiar with DSP, are familiar with electromagnetics, are familiar with optical communication. So I can pitch it at that level. Thank you. Thanks for the 21 participants who were, or maybe 22 participants who are listening. Thank you. You can lower your hands. Now, please raise your hands if you have questions, and please ask me questions. Okay. There was something about turbo codes somebody was asking in the chat. The turbo codes are useful for improving or for doing error correction. That will in principle not increase the capacity. That will allow you to reach the Shannon limit. So if you have a given SNR, you are supposed to get error-free transmission for certain spectral efficiency. But in reality, because of the errors in the channel, there could be bit erasure errors, or there could be some other errors, because of which you will never reach the Shannon capacity. So what turbo codes and LDPC codes and in general all the error correction codes do is for a given SNR, it will allow you to reach the Shannon limit, right? So I hope I've answered that question, right? So coding will help you only to reach the Shannon capacity, not if there is a gap between the achieved capacity spectral efficiency versus the theoretically expected spectral efficiency. That is what error correction codes will help you achieve. Okay, so you still need error correction codes on top of all of these things for achieving the best possible, theoretically possible, achievable capacity. Can you click again? So since we are kind of having this bottleneck where, no matter, what you do, you may not be able to increase this capacity. That is where this parallelism starts coming in, right? The first way of parallelism that starts coming in. And these are the, what you see on the left side are the most popular ways of transporting, or rather the top one, single core fiber is the most popular way of transporting information on an optical fiber. And this is the standard fiber that we know. It's a single mode fiber. Cutoff wavelength is 1280 nanometers, which means anything above 1280 nanometer is propagating as a single mode. And it has a core dimension of 10 micron, cladding dimension of 125 micron, and so on. Now, the next possible way of increasing the capacity, people thought, was why not use multiple modes? So instead of using fundamental mode, can you click again? Instead of just using fundamental mode, why not use the higher order modes, which is like a dumbbell shape mode, right? That is the LP01 A and B modes that I'm showing you at the bottom right. Why not independently encode these higher order modes and thereby increase the capacity, right? So that is one way of increasing capacity. And multi-core fiber is another way of increasing the capacity, where that's the third picture that you're seeing, where you keep all the modes as single mode fiber, but introduce more cores so that you are able to increase the capacity. And you could also think about few mode and multi-core together, right? Can you click again? The benefit of all this is that the Shannon's capacity theorem in these cases will become m times b log 1 plus SNR, where m represents, can you click again? M represents the parallel spatial paths. So if a few mode fiber, I'm using 3 modes, it will be 3 times B log. So you're basically increasing the capacity 3 times. And if it's a 4 core fiber, you're increasing the capacity 4 times. And if you're using a 4 core fiber with 3 modes, you're increasing the capacity 12 times, right? So this is one way of increasing the capacity by introducing what is called as parallelism. Okay. Now, the question is always that it is a lot of work to do this, because you need to make these fibers, you need to make them standardized, you need to install them, and that's a lot of practically challenging task. So we ask ourselves the question, why? Can you click on the next slide? Uh, why we are talking about parallelism in space, right? Why should we even talk about parallelism in space? Because, as I said, parallelism in space is a real lot challenge, right? So let's look at another parallelism which is possible in optical fiber. So that is what you're seeing on the left plot. You're seeing that you can use, sorry, you can use what is called as the C band and the L band, which are, different wavelengths, because we know that, as I said, all wavelengths greater than 1280 nanometer will propagate. Cutoff wavelength is 1280 nanometer. So any wavelength which is greater than 1280 nanometer will propagate as fundamental mode. So why should we restrict to C band, which is 1530 and 1560 nanometer? Why not move to C plus L band? Why can't you move to slightly shorter band, which is L band will be from 1580 to 1620 nanometer. S band will be from 1480 to 1530 nanometer. So why can't we look at parallelism that way, right? So if you look at the plot on the left, the bottom blue line, straight line, anyway, blue is, products that are commercially available. Red is research, right? And there's always a gap between research and actual product. Okay. Now, this plot on the left is showing for 100-kilometer transmission distance. Now, what does it show? It says that the bottom line actually shows what is the capacity achieved per wavelength, right? And the red, of course, is the research which is slightly higher than the blue. Okay. Now, the next set of lines, which is blue and red, and there's a yellow in between, which is a subsea cable, which is a cable that is installed in underground. There are so many other constraints in such cable, right? So what you are seeing there is, if I increase the number of channels, how does the capacity scale in this if I do C and if I do S plus C plus L, right? Now, it turns out that the WDM capacity per single mode fiber, whether it is in research or it is in product, is kind of saturating. They are just saturating above. If you look at the x-axis value, it is about 100 to 200 terabits per second. Research is saturating at 200 terabits per second. And if you look at the commercial products, that is like 100 terabits per second. Okay. So these are what are called as maximally achievable WDM capacity. Now, this is misleading because there is a fundamental trade-off between transmission capacity and distance, right? So if you look at capacities more than 100 terabits per second, that is limited to distances of 100 kilometer and below, right? So which means that this 100 terabits is achievable for only short distance. And for long distance, this doesn't happen. Why doesn't it happen? There are, again, the reasons are so you see the right side plot. You have the spectral efficiency dropping as a function of transmission distance. And why is it dropping as a function of transmission distance? Again, you start having nonlinearity coming into play, right? So there is a fundamental trade-off here. So even if you increase this S-band, the number of wavelengths, so that top left, the left side plot on the top corner has top left corner, basically explains the idea of WDM. You have multiple transmitters all getting combined using a wavelength multiplexer, and then there are demultiplexer and there are multiple receivers, right? So 1, 2, 3, 4, 5, 6, 7, 8 are just channel numbers there, right? So all this is leading again to the fact that even if you do increase in terms of parallelism, it's not in terms of wavelengths, the benefit may not be for very long distances. You will get a benefit only for short distances. Now you see the green line, which is kind of spiking up in the left side. That is when you use C plus L, and that is when you use multi-core fiber, where you increase the capacity in parallel, right? So turns out even in that respect, in terms of increasing the capacity to petabit per second, today's research challenge is how to reach 1 petabit per second, how to reach 10 petabit per second, how to reach 100 petabit per second, and how to reach those capacities at the longest possible distances. That is still a fundamental problem. Even though fiber seems to have a lot of bandwidth, you may ask the question, do you need petabit per second? And the answer is obvious, yes, because the way we are using data centers for all the AI, this petabit per second capacity over core networks are really, these days the people who are deploying fibers are not the traditional Tatas and Reliances. They are the data centers, the Amazons and the Googles are actually deploying fiber because they are doing their own fiber for carrying the capacity between their clouds, right? So this is really a problem, that the capacity crunch is a problem. Can you go to the next slide, please? So in space, as I already told you, the space division multiplexing has the possible scenarios where you could think of the first SDM space division multiplexing was introduced as SDM cables, not even SDM fibers. SDM cables would mean that you do have multiple fiber whose cladding or coating dimension is reduced so that you can pack more fiber in the same cable. That is an SDM cable. So there is nothing in the structural or cross-sectional change that is happening in this kind of fibers. Then you have multiple cores, multi-core fiber, and you have a multi-mode fiber. Now, as I told you, the possible, the bands for communication, the C plus L plus S plus U and so on. So, the hero results these days, if you go to an OFC conferences, they would talk about and they would actually talk about O starting from 1260, O to OESCLU bands, right? So that is like what is called as ultra wideband communication. When it is ultra wideband communication, meaning it is not to be mixed up with the ultra wideband in the radar parlance, it is for the communication parlance, optical communication parlance. Can you go to the next slide, please? So this is some, work that we try to assemble, with all of these, where are the, so there are 3 coordinates for each points. One coordinate is symbol rate. Second coordinate is number of WDM channels. And the third coordinate is a number of SDM channels. And this is something that we found from research papers from 1975 to 2025. Okay. And data rate per fiber is what is shown on the left side, right? So 10 power 6 gigabits per second, you can imagine what that is. That is the petabit per second. The 10 power 8 is again 100 petabit per second. So people have done, if you see the top right, maybe you can click again. Can you click once? So the highest symbol rate achieved is 260 gigabaud today. One WDM channel, one SDM channel, and you achieved something like some hundreds of gigabits per second. Can you click again? And from our analysis, we have seen people demonstrating 1505 WDM channels. That is all this S plus C plus L plus U plus etc. But their symbol rates are limited to 25 gigabaud. So they reached up to 1 petabit, close to 1 petabit per second. Can you click again? The third one is the highest space division multiplexing channel, right? So that is 114 space channels, 750 WDM channels, and again about 25 giga in the symbol rate. And they have reached, you see how the space division multiplexing is able to take one jump up, right? So wavelength is able to take see, you needed from 1 to 1500 wavelengths to take that step, but you would you needed only 750 WDM channel space channels to take it up by the same distance, right? So this is how the power of your WDM and the space compares. Okay, can we move to the next slide, please? Now I will talk about some of our some challenges with space division multiplexing and some results from space division multiplexing. Okay, so we can you click again? I think the clicks are not coordinated very well. So as I said, few mode fiber is fiber with a slightly larger diameter, and so slightly larger diameter would mean that there are more modes that can get supported. So there is a twofold degenerate mode, LP11A and LP11B, and each of the 3 modes can be you can use 2 polarizations. So there are 6 independent paths. So it is that M is actually 6 here, and so you have a transmitter 1 which can on the left side in the bottom plot. On the left side, you have a transmitter 1, transmitter 2, transmitter 3. So you can have 3 independent transmitters. And in each of them, you can have X and Y polarization. So you can have 6 streams of data. And then it passes through what is called as a mode multiplexer or a photonic lantern. And we still don't have a good way of making this photonic lantern. So if somebody is interested in doing some research, there'll be a good, nice research topic on how to make these photonic lanterns, which will take input as Gaussian, but it will convert them into the modes that we wish to launch into the few mode fiber, and a similar complementary device on the other side of the fiber where it will pick up all the 3 modes and put them back as Gaussian modes. So you have the transmitter and receiver will still operate with the Gaussian modes. Okay. So now can you click to the next slide? So don't click now, just leave it here. If you transmit these three modes in a few mode fiber, now the question we are asking is what will happen? What is the issue with this, right? So you will see that uh, you have the three modes don't start walking at the same time, in the sense that the group delay, the effective index of the modes are different. What is the consequence of effective index? You will see in that yellow patched region, the fundamental mode has reached a particular point in space, whereas the higher order modes have reached only this particular point. Actually, this representation is little incorrect because fundamental mode has the highest effective index, so it should be the slowest, and the higher order mode should be the fastest. So it is actually reversed, but that's okay. This is just representing the fact that the different modes are reaching the end of the fiber at different times, and this leads to what is called as intermodal dispersion. You would have learned intermodal dispersion in multimode fibers, right? Now, what happens if you have this issue? If you have this issue, if you know the intermodal dispersion, you can maybe correct for it. But if you think about it, is this now becoming a non-LTI system? These are kind of fundamental questions one can ask. Can you click again? If this intermodal dispersion is the only problem that can be solved, but what also happens is the mode starts talking to each other. They start mixing because the fiber is not kept straight. It could have bends in it. There could be micro bends in it. So what happens is energy starts multiple times propagating between the fundamental mode and the higher order. There's a continuous exchange of energy, information between the fundamental mode and the higher order modes. So that is represented as modal crosstalk here. Now, at the beginning, you will have energy in the fundamental mode. It will move to the higher order. It will propagate as a higher order mode. Then again, it will move back as a fundamental mode. So the modal dispersion is now not a single number. It becomes a statistics because it depends on how many times these modes have mixed with each other, right? So how do you model this? Can you click again? So this is how you model, right? So you have a output vector, which is a function of z and omega frequency. You do a frequency domain model for it. It keeps changing with the length, and that is related to the input vector through this coupling matrix, which is C, that tells you how this combine. And then there is a gamma matrix, which is a propagation matrix, which tells you what is a delay. And we know that the delay is a function of frequency. That's why that gamma matrix becomes a function of frequency. So the way you model this is that C, which is C11, C12, C13. So for example, C22, C12 tells you how much first mode couples with the second mode and so on. It's just a linear representation. And that gamma matrix tells you it's a diagonal matrix simply because it is just representing the delays. You see the first mode represents beta 2L. Second mode's speed is represented by beta 2L minus delta beta 1L. And the third mode is represented also as minus delta beta 1L because the second and the third mode are degenerate modes. They are degenerate modes, so their effective indices are the same, but their effective index of the second and the third mode is not the same as the effective index of the first mode. So this is the simplest representation of the coupling matrix and the propagation matrix. But in reality, how does it look like? Can you go to the next slide, please? This matrices, if you multiply, just go to the previous one. Go to the previous slide. So you have that C and you have to multiply that with the gamma. So finally, if you look at, go to the next slide, please. If you look at three mode fiber, and as I told you, three mode fiber would actually mean that 3 times 2, you have two polarizations. So the coupling matrix is actually a 6 by 6 matrix, not a 3 by 3 matrix, right? So that 6 by 6 matrix, the diagonal sub-diagonal matrices at C11, C12, C21, C22. Similarly, that's shown in red, right? So those are representing mixing between the polarizations of the same mode. Then there is a blue matrix, which is between the mixing between the, which represents the mixing between the degenerate modes. And then there is a green matrix, which is representing the mixing between the fundamental mode and the higher order mode, right? So these are what we call as polarization coupling. Then you have mode group club coupling, and then you have strong coupling, right? Now, the statistics of when polarization mixing is happening, at what distances mode groups are mixing, and at what distances the degenerate modes are mixing, that statistics is kind of known. And what is known, that known is, what is known is, so what we have done is we have shown some bar graphs. What does that histogram show? That histogram shows how many times will you have polarization coupling. If I take a long length of fiber, how many times will you have, for example, the top red graph shows how many times will you have mixing at every 10 meters. The mean is around 10, you see. Around 10 meters, every 10 meters, there is definitely the, it's most probable that, it is most likely that after around 10 meter, definitely the polarizations have to mix. So you call them as what are, what are called as coherence lengths for polarization coupling. If you see the mode group mixing, it is about 200 meters. It's like kind of flat. It is all statistical. And these are all, there is also a strong basis of what statistics and how this gets generated. I'm not going to get into those. And you see about 1 kilometer, 900 meter is where the strong coupling happens. So which means there are 3 length scales over which this happens. Every 10 meter, polarizations mix. Every something like 200 meters, the degenerate modes will mix. And every 1 kilometer, all the modes will get mixed. So if you have a length of something like only 100 meter, you need to worry mostly only about polarization mixing. If you have a length of kilometer, then you have to worry about all types of mixing. So that is the statistics of mixing. Now, what about the statistics of the group delay? As I told you, the modes as they propagate, turns out that the group delay is also a function of distance, right? And that gets decided by the delay between the modes. That's also a function of distance. In fact, it's a function of position, not distance, I should say. And what is defined is its autocorrelation function. So we found that statistics, that autocorrelation function is known to be, in the second line it is written sigma square exponential minus mod z by LC. That's again a coupling length or a coherence length for the group delay. That is known, that is statistically known. So we can construct the randomness of how this group delay is fluctuating along the length of the fiber, right? So if you see on the bottom right plot, we have plotted this for different coherence lengths. The last one is for 100 meter, then it is 10 meter, then it is 1 meter, then it's 0.1 meter. If you see the coherence length is 0.1 meter, fluctuations are very fast. I mean, in terms of length. If you look at 100 meter, it's like a slow fluctuation, right? So you can characterize this for a fiber. So you can completely characterize the statistics of coupling and also the delays in a few mode fiber. Can you move to the next slide, please? Now, once you characterize that, we can go ahead and simulate this whole impairment, right? So in addition to the impairments that are what are called as common mode impairments, which is true for any coherent system, you do have frequency offset, group velocity dispersion, laser phase noise. These are all common impairments in any optical coherent communication system, right? But in addition to that, if you are using a few mode fiber, we have what are called as mode dependent impairments, the impairments that we just saw, this coupling and the modal dispersion. So there are standard algorithms that are possible. This is why I asked how many of you are working in signal processing. if you are familiar with signal processing and if you have some knowledge about signal processing, you can think about algorithms which can be used for undoing all these impairments. So for example, for group velocity dispersion, there is a frequency domain equalization possible. For frequency offset correction, there is a periodogram technique that's possible. Laser phase noise, there are a couple of methods. Is simple decision directed LMS or a Viterbi algorithm that is possible. For coupling, modal coupling and modal dispersion, you need a MIMO, multi-tap MIMO equalizer. Now, some of the structures of the signal processing is shown here, but what is more interesting for you if you want to do research in this area is that all of these can now potentially be replaced by neural networks, right? Now you need to choose the right kind of neural networks to uh, uh, structure this so that the entire statistics is captured. That's a very green area of research. And again, I warn you, please do not mindlessly apply any neural network algorithms on this. Please make sure that you know what you're doing, what algorithms you have to what kind of neural networks will work for different kind of problems. At least in this work, I'm not going to show you any of our results on machine learning, but it is generally, we call it in the domain of statistical signal processing. Can you go to the next slide, please? So you have the model, the mathematical model is this: y equal to is your received vector, h is your channel matrix, s is your input signal, and n is your noise. So y equal to hs plus n is what you receive. What we are always trying to get is from y, we are trying to reach s. So we will always have a minimum mean squared error equalizer, which is s bar, which is some w times y. So essentially the hope is that you find the right w, which you will multiply with y to get s bar. S bar is the closest approximation to s, right? So that y is again hs plus n. Now you work on what is called as a decision desired your signal vector d. That is what I am looking for. That error between my signal vector d, the difference between the two is my error, and I want to optimize my weight matrix, that W matrix, such that it is minimum of J matrix, that's J, which is your cost function, times, or rather, which is a function of W, and that is trace of E expectation of H bar. So essentially, you use the gradient descent method, right? Or we could use data in this. So the standards allow pilots to be used. So we do use data. So you use the gradient descent method where you keep updating these weights W. W of k plus 1 is the previous weight plus mu times, which is your step size, error times exponential j phi y of the current received signal. So this is the structure. You can implement this filter. Can you go to the next slide, please? And after implementing these structures, this is what we got from an experimental data if we use a 3-mode fiber, right? So you have, in fact, this is an example of, I think, only 2 mode, not even 3 modes, okay? So there are several DSP steps, as you see. Each one of them is to be implemented in a very careful manner. Every time the step sizes have to be optimized. The sequence of algorithms are important, and how you implement these algorithms are also important. And as I said, there is a minefield of research that can be done if we can replace these with neural networks. Can you go to the next slide, please? And this is our BER versus OSNR. With theoretical is what is shown in black. With single mode fiber is what is shown in blue, which tells you how optimal is my experimental setup. There is a 1 dB difference between the Shannon limit. Then you have back-to-back for a multi-mode, because we did not have so many receivers. So there was some time division multiplexing that had to be done. So that created some errors. And then for 1.4 kilometer fiber, you have the red. So essentially, successful demodulation was done with this approach of our DSP. Can you move to the next slide, please? This approach was okay. There was no problem about it, but it required a lot more DSP than a regular coherent system. So we moved on to the next possible way of parallelizing, and that is with space division multiplexing, and that is with multi-core fibers. Can you go to the next slide, please? So here, okay, so one question I have, or do you have any questions until now? Because we are moving to multi-core fibers. Are there any questions or concerns or? Okay, then I'll move on. As I said, the next way to look at it is next SDM fiber is the multi-core fiber. So here again, we are trying to see even in multi-core fiber, there could be fiber with coupling, there could be fiber without coupling, right? So you could have, this is a picture from Sumitomo, where they show that if you look at figure B, there's a multi-core fiber which is uncoupled, which means it just acts like a parallel path. There is a multi-core fiber that could be with interference because that's where the cores may be closer to each other. So there could be a crosstalk between the cores. There could be a multi-core fiber which is randomly coupled, which means that coupling happens all the way along the length of the fiber, which will require a MIMO receiver. If it is just interference, you may do with minimal crosstalk. And then you could have a multi-mode fiber where you could have all the cores coming, mixing very, very large, and then you will again need a MIMO receiver, right? So can you do 3 clicks? Okay, so as I said, this D type of fiber, which is a randomly coupled fiber, the power consumption is proportional to the length of the filter used in MIMO DSP, and the length of the filter function is proportional to square root of L, which just means that if you are using, so why should I use randomly coupled core fiber if I have an uncoupled core fiber which is perfectly well? So there's a small catch there. The benefit of randomly coupled core fiber is that I could put all these fibers very close to each other. So I allow them to couple. Whereas if it is an uncoupled fiber, I need to keep the cores at a specific distance so that they don't talk to each other. So the number of cores that I can introduce given a cladding dimension is going to be very small if it is an uncoupled core fiber. Whereas if it's a randomly coupled core fiber, for example, in 125 micron cladding, you could put as much as, I think 19 cores or something, right? So, but the problem is that they will couple. So what is the length of the filter that you need to use? As I showed you earlier, it just keeps accumulating with the length of the fiber. So the length of the filter function is actually coming out to be proportional to square root of L, right? So the consensus right now is that for short distances, you use uncoupled core fiber so that you don't have to do any kind of complicated signal processing. Whereas for long distance fiber, you are going to do anyway a lot of signal processing because there is dispersion, there is nonlinearity, and then you want to increase the capacity in long distance. So you are removing this constraint of adding the DSP. So you will use the standards are considering randomly coupled core fibers for long distances, while for short distances it's uncoupled core fiber, right? You see the number of multipliers that you see, how much benefit that you are able to get if it is a 19 core fiber versus a 55 mode fiber, right? So if I go by the few mode fiber way, and if I'm using a 55 mode fiber to get 1.53 petabit per second, the number of multipliers, the number of MIMO filter multipliers that I need is about 10 power 5. But if I use a 19 core fiber instead, I can reach 1.7 petabits per second with only 1000 multipliers for a transmission distance of 100 kilometers. But you see the gap starts increasing as you increase the distance. The number of multipliers, because of that square root L factor, right? The number of multipliers starts dropping. So it is always good to go for number of cores, larger number of cores than larger number of modes. Can you go to the next slide, please? So what does, you can click some 4 or 5 times until you reach the end of this slide. Right? So what you really see is all the 4 modes are propagating. I just want to distinguish this from the previous case where I said that these modes are propagating with different speeds. Here, all the modes are propagating with the same speeds because these modes are not really modes of the same core. These are fundamental modes of a single core fiber, right? So there is no reason why their propagation constants are going to be different, right? And their polarization mixing can be modeled as polarization mixing matrix, root alpha e power j delta. That's like a unitary matrix that represents the amplitude and phase difference between the two polarization. And there could be crosstalk in these fibers also. So crosstalk could be an issue, and there could also be polarization mixing. So what we are saying is that we want to in the signal processing matrix, we want to deal with crosstalk and polarization together. So what I'm going to show you is some method to generate. Can you click once more? Once more. How to generate these crosstalk matrix, which could be based on Kronecker product or it could be based on random matrix, right? So I'm going to show you what this crosstalk is we are talking about, because I already told that multi-core, there should not be any crosstalk ideally, but practically, why do you have crosstalk? So that's the next slide, please. You see that the main major reason for crosstalk is bend induced perturbations. So if you bend the fiber, so the top left you see a picture where there is a green dot and a red dot. The green and the red dots are the positions of the core. The corresponding refractive index is what is shown in the bottom, right? So you have the refractive index profile, and you have a, let's say, a slight difference between the effective indices of the two modes, just to kind of amplify the effect. Now, when you bend, what really happens is there is a curvature. When there is a curvature, the conformal mapping of the refractive index profile is what is shown in the second picture, where you see that the refractive index profiles are tilted. So what does that tilt represent? If I bend the fiber, it is as if I am tilting the refractive index. So we can solve the modes for this tilted refractive index profile. And then if you are bending the other direction, the tilt is towards the other. So what happens is there could be the effective indices of the two modes, because of one tilt, could separate out, or depending on the tilt, it could match. And when the effective indices match, it just means that the modes start coupling to each other. They start talking to each other, right? So these can happen randomly along the length of the fiber. And wherever you see the effective indices crossing, on the right side picture, you see that the blue and the red, there is a crossover. That is what is called as a phase matching point, where the effective index of the mode in the core M becomes equal to that of in the core N. And because of that, as a function of propagation distance, you see one crosstalk jump there, right? The crosstalk starts increasing. And along the length of this fiber, there could be multiple places where these effective indices match because of random bending. And because of that, the crosstalk starts increasing with length. Now, can you model this? Yes, of course, you can model this. So you can write the propagation equations of the two modes in the two cores as dAn by dz. That is the amplitude of the standard coupled mode theory. So you say that is the amplitude of the mode propagating in the nth core is resultant of summation over all the m cores, and kappa is the coupling matrix, and e exponential j beta n minus beta m will give you the effective index differences. And of course, it'll get summed over all the modes. So can we go to the next slide, please? So you can, so how do we do this modeling? So we say we wanted to actually model this crosstalk given any arbitrary refractive index. Okay, so this is more like, how do I build a multi-core fiber? What should I do to build a multi-core fiber, right? So you start with two types of multi-core fiber. So you don't do a simple step index profile. You use what is called as a trench profile. Why do you need this trench profile? You need this trench profile because you want to confine the modes so that you don't want them to mix with each other, right? So trenching helps to confine the modes. So you see there is a core, and then there is a trench, and then there is a cladding. There is another trench type where there is a core, then there is a cladding, and then you do the trench, right? Both of them are popularly used by fiber designer. So first step in this model is that you define the refractive index profile. In the second step, what you're doing is put this refractive index profile in COMSOL kind of simulator, find out the field, the modal field corresponding to this refractive index profile. Go to, click once more. Then you move to MATLAB, where you now you know the modal profile. From the modal profile, you can find the overlap integrals and find out what is the coupling coefficient. So that is the third step. And the last step, can you click again, is to find the crosstalk, because once you know the coupling coefficient, you can put it back in that differential equation and find out the crosstalk. Can you go to the next slide, please? So here is the details of the math there. So along, if you see on the figure on the right side, along the length of the fiber, we have introduced a perturbation, that random perturbation, and it is also bent with a bending radius, and bend direction is also randomly chosen. So you do have a kappa nm, and you do have an fz, which is a random phase function, which is representing all the random phases along the position z. You calculate the coupling coefficient as an overlap integral between the mode m and mode n, and you would, this kappa mn is coming from a standard coupled mode theory, which is a fundamental coupled mode theory in any photonics textbook. It is the same thing. And we also added twisting, bending, and random perturbation, right? So we have 1, 2, 3, 4 cores, and we took a core pitch of 40 micron, length of 10 kilometer, because remember, crosstalk will keep accumulating with length. We took a spool radius, standard 85 mm spool radius. We said the fiber could have been twisted while winding, so that could be a winding rate or a twisting rate. And there's some correlation length for this random perturbation, and that's 0.1 meter, something coming from fabrication tolerance. Next slide, please. With this and the strategy that I told you, going between COMSOL and MATLAB and solving the differential equation, we got the crosstalk variation between adjacent core and diagonal core to be different, which is to be expected, because if the cores are diagonals, they are far away, and adjacent cores are nearer. So the adjacent core crosstalks are bunched at a slightly higher value, and the diagonal core crosstalks are at a lower value. One is A is without trench, B is for the type 1 trench, C is for the type 2 trench. Now, you see that black dot in those plots, those are the measured values. So these are fibers that our collaborator, who is Sterlite Technologies, they had manufactured, and we measured the crosstalk from these fibers. So we basically modeled the fibers, they manufactured it, and we measured the crosstalk. And this is a very good testament that we are able to accurately predict, or now we could accurately design for any desired crosstalk, right? And we of course found that trenching improves the crosstalk. Type 2 is minus 60 dB, we got type 1 is minus 40 dB, and without trench is minus 30 dB, right? So definitely one should go for trenching. Can you go to the next slide, please? Now there are, other trench parameters. Maybe we can skip this. This is more of details into the design of trenching. How does the trench width affect? How does the trench height effects and so on. Can we move to the next slide? Now we do transmission, right? So we say, let's try to do transmission of data in this setup. So you have signal IQ modulator. Can you do 2 clicks? Right. If I have two, core transmission system, I have a 4x4 matrix because I do have polarization mixing. So this is your coupling matrix. And if there is mixing, the MIMO filter looks like what is shown on the right side, right? Can you give 2 clicks? And this seems to be extremely complex. So now we moved our attention to DSP and said, okay, can we look at some smaller complexity, right? So one interesting thing we found is that these elements are not independent of each other. I'll explain that. Can you go to the next slide, please? You see, when I created a disturbance in the multi-core fiber, so I had 2 lasers. I am sending information into a multi-core fiber. I do some disturbance. I just knock the multi-core fiber and I look at polarization diverse power measurement at the output. So I take the power out of core 1 and core 2 and look at what is the power in X polarization and what's the power in Y polarization. So power meter 1 and 2 measures the X and Y polarization power in the core 1 because it is measured through a polarization beam splitter, and the power meter 3 and 4 would measure the power out of polarization diverse measurement out of core 2. Can you click once? What is seen is that as a function of time, we kind of automated these power meters and started looking at what these powers are telling us, right? So the blue one on top left says the power in power meter 1. It is dipping every now and then based on, so somebody is continuously knocking this fiber. So whenever it gets a knock, it power dips. But you see the black curve actually shows a same pattern which is increasing, which means when the power drops in one polarization, it actually moves to the other polarization, which is not surprising actually, right? But what is really surprising is that if you look at power meter 3 and 4, there is a correlation between the power transfer between the cores as well, right? So these are results of different trials, and the power fluctuation in the 2 polarization in both the cores are correlated. So that gives us a hope that we will be able to minimize the signal processing functionalities, right? So can you move to the next slide, please? So we will now see how to use this information. So we know the polarization matrix is given by the left side, and the crosstalk matrix is given in the right side, where beta in the right side represents the power transfer between the crosstalks, right? Now you have both polarization mixing and crosstalk matrix. So what we can do is just one click, please. You can think about the final mixing matrix as a Kronecker product between power polarization mixing and crosstalk. Now, what is this Kronecker product? If you've forgotten in your linear algebra, I have a definition for Kronecker product. One click. Let's say you have a matrix C and you have a matrix P given by C11, C12, C21, C22, and Pxx, Pxy, Pyx, and Pyy. Then one click. Kronecker product C, Kronecker P is you expand P into C, right? So C11P, C22P, C21P, C22P. So it is not a standard product, it's called the Kronecker product. So it's like saying that the same polarization matrix is creeping into all the crosstalk coefficients, right? So we demand that the final mixing matrix is actually a Kronecker product and it is not a regular product. Now, what is the benefit of doing this Kronecker product? Now you have to do 3 clicks. It is supposed to be a regular product, but the moment you make it as a Kronecker product, you think about it as a Kronecker product, we have the relations that are written on the right side, that C11 equal to Cij, I equal to j, I, all the C1s are equal. C12 is my, C11 is not equal. All the C11, C22, C33, C44 are independent, but C12 is minus C21 star, C34 is equal to C. So you get a lot of relationship between these elements. And what is the benefit of that? Instead of calculating all the 16 elements of the matrix, it's enough to calculate only a few of them and the others can be found out, right? So this is the benefit of, so I told you physically why when you disturb a polarization, how that disturbance gets transferred across the core. And because of that, you're able to write it as a Kronecker product. And because you're able to write it as a Kronecker product, your DSP is minimal. So this is how, so this was interesting for us because we could translate some knowledge from the experiment directly into linear algebra and, carry out some interesting experiments. Can you go to the next slide, please? Click again. So we did some simulation results here. We said, okay, let's try 56 gigabaud PM16 QAM with a laser line width of 100 kilohertz, fiber length of 80 kilometer, frequency offset of 500 megahertz. And we looked at what is the DSP in the receiver side. We did the crosstalk and polarization demultiplexing together, and we could get everything perfectly fine. Okay. But what if, the next slide, please. What if the fiber doesn't behave that way in reality? So we started looking at how do I now use a random matrix based crosstalk model. See, it is very easy to generate random numbers, but if you want to generate random matrix, it is not really a straightforward thing, right? And you want a random matrix, not just any random matrix, a random matrix which will give you a specified crosstalk. So that is something we worked on, and I think you can move to a couple of clicks, 2, 3, 4 clicks. Yeah. So to model, next slide. Yeah. So this is the recipe we found, that if I were to generate any random crosstalk, what I should do is I start with what is called as epsilon, which is my control parameter. Then construct a 8 by 8 matrix because I want an 8 by 8 matrix. Then you define a construct a matrix which is 8 by 8, which is made of random numbers. Then that random, if I just put in random numbers in a matrix, that won't be unitary. And being unitary is important because my energy has to be conserved. Whatever power one core loses, it should be found in another core. So if you just put random numbers into your matrix, you won't achieve that. So you define a matrix X minus X prime, which is antisymmetric because of the way it is defined. And to get the random unitary matrix, you do an exponential EH, that is matrix, what is described there. And then the coupling matrix is M times C. Right. So with this method, we got, for example, crosstalk of minus 38 dB. This is how the matrix looks like. The elements of that matrix looks like. For a crosstalk of minus 9 dB, there is minus there, minus 9 dB. You see the cores have started mixing with each other. Next, at least 4 clicks. Yeah. And with these matrices, if I don't have this polarization or and core relation, if I don't have this Kronecker product equivalence, then I would end up with solving 64 coefficients in an 8 by 8 linear MIMO matrix. We also did that. Next slide. 2, 3 clicks so that you complete. Yes. So you say that for this kind of structure, we constructed the DSP for 56 gigabaud PM16 QAM, and we were able to recover the constellations. Right now comes reality. Can you go to the next slide, please? Experiment. Now, what happens in experiment? All this was nice simulation, right? So this experiment was done in Sterlite Technologies because this is a time where we did not have our equipments ready yet. So we used their multi-core fiber and used single transmitter, decorrelated it, taken it through 13 kilometer of multi-core fiber, received the output. Couple of clicks, please. So we found that the crosstalk, so that blue colorful thing is the crosstalks, right? You found that in reality, the crosstalks between core 1, 2, 3, 4 are very different. For core 1, core 4 is a diagonal core, so that has least crosstalk. The adjacent cores, the crosstalk are quite large, which is minus 30 or minus 20 dB. And even with that, we could actually, through our signal processing, we could actually transmit very high data rate. In this case, 42 gigabaud, so it comes out to be 1.24 terabits per second, right? Next slide, please. Now, what do you do if you have longer lengths of fiber? So we use what is called as a recirculating loop. This is a product built in IIT Madras only. You see that this is a way you can circulate the data through a short length of fiber multiple times to emulate long length of fiber. So it's basically a switching system that does this. Next slide, please. So we also try to do bidirectional transmission because one of the Google's deployment is for bidirectional transmission. So we did bidirectional transmission with a multi-core fiber with a recirculating loop, and this was very successful. Go to the next slide, please. Next click. Sorry, previous one. Just to tell you that the transmission parameters, we'll go to the next slide, which has more details. And we said the crosstalk is quite bad, right? So what is the impact of this crosstalk? So we compared multi-core fiber with a single core fiber. And what it tells you, these plots tell you, on the middle plot tells you, the second plot tells you is that the red is the predicted crosstalk, right? So this is where the crosstalk goes from minus 24 to minus 14, right? And the blue x-axis is length of the fiber, y-axis is bit error rate. So smaller bit error rate means good, larger bit error rates, higher bit error rates means bad. So single core fiber, we took a 40 kilometer single core fiber and 4 times 10 kilometer of multi-core fiber, that is 10 kilometer of multi-core fiber, which is shown in round. You see that the BR performance is almost identical up to about 320 kilometers of transmission length, right? But beyond 320 kilometers, you see the single core fiber is still kind of saturating at 10 power minus 5, whereas a multi-core fiber, the BR is going worse and worse and worse. And that is because there is crosstalk, and we did not use any MIMO DSP to correct for this crosstalk. The same can be shown as a constellation. If you click once, as at 160 kilometer, you cannot distinguish between MCF and SCF. The top is MCF, bottom is SCF, single core fiber. Whereas when it is 400 kilometer, MCF looks way bad when compared to SCF. So where are we going with all this? Why are we doing all this study? Because we want to actually commercialize multi-core fiber, right? Can you go to the next slide, please? So we have a complete multi-core fiber ecosystem built around the AOC testbed project, Advanced Optical Communication Testbed Project consortium, where we are, I've already told you Sterlite is making the fiber, they are making the cable also. We built the FMS units, we are building the fan-ins and fan-outs with industry partner. We are also building transceivers. So the entire ecosystem for multi-core fiber is being developed in this testbed project. And not only we build this multi-core fiber cable, can you click once? It is deployed on IIT Madras campus. So this is the Google map of our campus. On the top, you see a hut there. That is actually the main gate of the campus. And you can follow the line green, yellow, and red. And finally, it ends in another yellow hut. That is our lab. So from the main gate to our lab, there is a yellow line which represents multi-core fiber, which is deployed underground. There is a red line which represents the multi-core aerial fiber, which is also deployed as an aerial between posts. And from the last blue section tells you that how it reaches the lab, right? Can you go to the next slide, please? So what we deployed is, I mean, just to give you a reference, what Google and NEC are doing are 2-core fiber, right? Just to give you a point of reference. Can you go to the next slide, please? Whereas we are doing a 4-core fiber. So these are pictures from our campus where all the junction boxes that you see are the terminations of multi-core fibers. Next slide, please. This is the transmission test bed because you have 4 cores. So you do have termination fibers on the top right towards the field. You see the fiber cable going through the wall and it is reaching the field. On the right side, rightmost rack, you have all the termination boxes. The second rack has all the 4-channel coherent receivers. The middle rack has all the transmitters and also a 320-kilometer fiber. And the first 2 racks actually have a very high speed transmitter which can run up to 100 gigabaud. Next slide, please. So I welcome you. This is how our lab looks like. So we can think about constructive experiments in the lab. And all of them are remotely connected. All these transmission racks are remotely connected from different tables so that we can always work at different tables and access to the racks. Next slide, please. Just to give you reference of where are we when compared to the other rest of the world and also what other people are doing with a multi-core fiber. I will not get into the details. When you have multi-core fiber, you can do quantum key distribution and establish classical and quantum coexistence with multi-core fiber. Next slide, please. There is another demonstration in Guangzhou where they have deployed multi-core fiber over short distances entirely for the purpose of integrated communication and sensing. So this is an example for that. And I have my last slide. Next slide. Oh, sorry. Next slide. Sorry, this is some kind of repeat. Sorry. Please keep clicking. Yeah, this is my summary slide. I've already shown you those previous pictures. So just to summarize, parallelization in space is helping you with disruptive methods in capacity scaling. We could do ultra wideband and multi-core for establishing research capacity, establishing higher capacities. We could do a lot of machine learning to correct for all the impairments. And it is a very nice meeting point for sensing, people working in sensing, people working in QKD, and people working in communication. So with this, I conclude and I welcome you to come and use the testbed facilities at IIT Madras. As I said, we have the field deployed fiber, we have all the transmission equipments. So if it is for data collection for your ML algorithms, if it is for trying simple signal processing, there is no limit to what you can imagine. So you are welcome to use the testbed at IIT Madras. Thank you.
Thank you for the clear, insightful, and interactive session. And now I request to all the participants, and if they are having any query, they can type in the chat box. But for us, any question?